Saxon's Trig, lesson 39, beginning on page 277, is about radian measure for angles, forms of linear equations. So earlier in just a couple lessons ago, I said that there will be multiple forms of lines, and that's why they were clarifying the point slope form. So that's what section B is going to be about, is all of the other forms, hopefully review for most of you. All right, but before we get into that, radian measure of angles. So everything we've done so far, we've done in degrees, 30 degrees, 60 degrees, 90 degrees. All of our information was in degrees. And so when we did our 4-quadrant grid, this was 0, 90, 180, 270, and 360, and all of those were in degrees. Now what they're giving me here is another way to talk about these, not in degrees, it's in radian. Now your calculators have a way to, and they should be by default set at DEG for degrees, but there should be a rad section, whether it's embedded in a menu where you can change it over so that it understands that it's not calculating in degrees, it's calculating in radians. But we don't want to always rely on our calculators to do stuff because we may not always have access to our calculator. So let's talk about how we convert from radians to degrees, but before we do that, let's talk about what radians actually are. They will always have a pi in their answer. So the new Cartesian plane for radians will still be 0 radians because 0 times pi is still 0. But the 180 is actually pi. That makes this one pi over 2, and this one 3 pi over 4, and this one, a full circle, is in 2 pi radians. Now I'm not gonna, like with degrees we have the little symbol. Radian, we're not gonna write rad with every single one. If you're seeing it with a pi symbol, you know that you're in radian mode. So the one that we memorize, the simplest and easiest one to do conversions from degrees to radians, is the 0 and the pi. Pi over 2 and 3 pi over 4 are in fraction, and that's why they're not as easy. So when I want to convert, I'm going to use as the fractional form pi over 180 or 180 over pi, just depending on which way I need to cancel pieces out. So these are the conversion facts that you're going to use. And I would have that in my notes, that to go from degrees to radians, these are the conversion facts we're going to use. I would also make sure that you should have had this one from before, and now this one you're going to have from for the radians. So this is the new one that you need to have jotted down. All right, let me see here. Yeah, now that we've talked about it, let's now do example 1, do what you need to do, which is 4 sine of pi over 4 plus sine of negative pi over 3. So before I graph these, I know what I started to say a moment ago. Some of you, especially if you came from another school, you were probably provided with a chart that showed you in circle format every single degree matching with almost every single radian, or at least the key ones like 45 degrees, 30, 60, and all of those going around. And if you have such a chart and you wish to use it to do your conversions, that's fine. I'm going to go through this convert and then graph it in degree every single example that I do. So my first thing that I do is I don't want to work in pi over 4 because I don't know what that is. So I'm going to change pi over 4 to degree. I want the pi to cancel, so I'm going to put the pi down in the bottom, and I'm going to use this conversion fact with the 180 in the top. Pi's will cancel off, that's why I put them in opposite spots, and 4 divides into 180. Let's see, 4 goes in there, 4, and then, yes, so that should be 45. So now, ultimately, what we're doing is 4 sine of 45 degrees plus sine of negative. Let's do the same thing with our pi over 3. So since I wrote the negative here, I'm going to just leave that off of my conversion. We want the pi to cancel, goes in the bottom, 180 in the top. pi's cancel off. 3 divides into. You get to do these pretty quickly after you've done a bunch of them. So 3 into 180 goes 60 times. So this is negative 60 degrees. Now you're back to doing these problems exactly as we were before. So graph 45 degrees, which means 1 root 2. And because that was memorized, I'm going to do my changing this thing. So they gave me a hypotenuse of 4. So this times what should ultimately turn it into 4? I want the root 2 to go away. So that would be definitely a root 2. Ooh, that's tiny. And that would give me 2. 2 times 2 would be 4. So 2 root 2. So if I multiply this one by 2 root 2 and this one by 2 root 2, I get for this answer 2 root 2 and for this one 2 root 2. Okay, so technically I would be having here 2 root 2i plus 2 root 2j in its polar form. Yes, okay, plus, and then you need to do this other one, all right? So graph, negative going this way, 60 degrees. Now, could you have done the sine and cosine times 4 thing? Yes, and that's going to give you the decimal formats of these, and maybe that is the better way to go. It just kind of depends on how they want the solution, and I'll try to turn the page and look and see here how they actually did it. But either way should be fine. Opposite the 60 is root 3, negative because it's going down. Side would be 1, hypotenuse of 2. And it wants sine, opposite, so opposite over hypotenuse. So the opposite is, oh, you know what? Because I'm adding this. Oh my goodness gracious, I completely shifted gears here. I'm adding vectors. No. I do want opposite over, okay, I'm gonna fix this one in a split second. Opposite is negative root 3 over hypotenuse of 2. That's that one. Scratch this. Oh, let's go back. Sine of this 45, oh my goodness, opposite over hypotenuse. Opposite is 2 root 2 over hypotenuse of 4. And those are adding together. Oh, that's so much easier. Yikes. Okay. Yeah, we were definitely not adding vectors. If we had actually been live in the classroom, you would have been flagging me down and saying, wait. Common denominator of 4 means this one multiplies by a 2. These are not the same, so I'm not going to be able to combine them. So it's going to be 2 root 2 minus 2 root 3 all over 4. Ooh, but all 3 of those outer ones will reduce. So root 2 minus root 3, so I'm dividing everything by 2. And now let me turn the page and see if we're in the ballpark of what they're looking for. Oh, they left it at, either I made a mistake or, because they say their answer added together is 4 root 2 minus root 3. Well, I'm on the track there. All over 2. It's something with this one. All right, I'm going to pause it, find my mistake, and then tell you where it is. I'm pretty sure I instinctively did an adjustment that I shouldn't have done here when I found this is a multiply by 4, not trying to change the hypotenuse. So this needs to remain exactly as they were originally, 1, 1, and root 2. The sine of 45 is 1 over root 2. That's opposite over hypotenuse. Multiplying by the 4 makes it 4 over root 2, and that's clearly where I've gone awry. So this should be technically at the moment 4 over root 2. But I want to fix this root 2. So that's going to multiply by root 2 over root 2. 4 root 2 over 2. And that could reduce. However, before I change this to a common denominator of 4, it already had a denominator of 2. So let's leave it in that. Let's get rid of that. So common denominator is 2. So this is 4 root 2 minus root 3 over the 2. Aha! Now I match with their answer. Okay, yep, so I just instinctively did something there that I shouldn't have been adjusting. And you're not going to instinctively have that problem. Let's see if we can do example 2, clarify all this radian stuff without confusing you with error on my part. Evaluate sine of 13 pi over 4 plus 3 cosine of negative 5 pi over 3. And that one's in a parenthesis because of the negative. So I'm going to first convert 13 pi over 4 with pi and 180, so they will cancel. 4 goes into 180 45 times. And again, once you've done enough of these, you get that memorized. And then 45 times 13 is going to be 585. So we're doing sine of 585 degrees plus 3 cosine of, and let's convert negative, I'm going to leave the negative off, negative. So 5 pi over 3, pi to cancel, 180. Cancel the pi's, 3 goes in here 60 times. 60 times 5 is 300 degrees. Graph. This seems to be more than 360. So we need to subtract off 360. And I mentally just checked, should it wrap twice, which would be 720? No, because that's more than, so I'm not having to do a double step. And that should be 225 degrees. So 0, 90, 180, 270. I didn't quite reach 270 to get the 225. How much past 180 is the 225? 45 degrees. So negative 1, because of the quadrants, root 2. Sine is opposite over hypotenuse. So the opposite is negative 1 over root 2 plus, and now we'll work on this one. Negative means I'm going to go this way, 0, negative 90, negative 180, negative 270 in quadrant 1. I'm shy of 360 by 60 degrees because I went negative 300. And opposite 60, root 3, adjacent 1, hypotenuse 2. That's labeled. Then I know that here I will have 3 times cosine ka, adjacent over hypotenuse. Adjacent is 1, hypotenuse is 2. Then this one needs to fix its denominator, so negative root 2 over 2 plus multiply 3 over 2. They already have a common denominator, but they're not like terms. And just because I want the root last, I'm going to write this as 3 minus root 2 over 2. Checking their answer. Oh, they kept it, of course, negative root 2 plus 3 over 2. Either way, I still have the 3 as a positive and the root 2 is a negative. Oh, we're good to go. Example 3. Cosine of, at least I didn't make a major error, so hopefully this is clicking a little better for you. Negative 25 pi over 6. They kept it in a parenthesis because of the negative. Minus 2 tangent of 4 pi over 3. All right, negative 25 pi over 6. Pi is going to cancel. 180 is its match. Cancel the pi's. 6 goes into 180 30 times. 30 times 25. Oh, and again, that negative I didn't have to keep over here. So it's going to be cosine of negative 0, 15, 750? Yes, okay. Minus 2 tangent of, all right, convert 4 pi over 3. Pi cancels, 180 on the top. 3 goes into 180, 60 times. 6 times 4, 240 degrees. Now we graph, oh, that should have stayed in parentheses. We graph negative, so 0 going this way, and that's more than 360. And doubling that is 720. So I'm actually wrapping twice. So I'm going to minus 720 and only keep 30. So negatively once, negatively twice, and then 30 more lands me in this quadrant. Opposite of 30 is 1, and it's going to be negative because it's going down. This is root 3. Hypotenuse is 2. cosine ka, adjacent over hypotenuse. So my adjacent is root 3, hypotenuse of 2, minus 2 multiplying with, now we need to graph 240, 0, 180, 90, 270, it's before that. So how much past 180 is the 240? 60. So opposite of that is root 3. That's negative because of the quadrant. This is negative 1 because of the quadrant. Hypotenuse of 2. Tangent is TOA. So the opposite is negative root 3 and the adjacent is negative 1. Those two negatives are going to make it positive. Let's just rewrite root 3 over 2 minus 2. And then let's fix this to its positive form. And root 3 over 1 is basically root 3. Then I realized that to put these together, I need a common denominator, so let's make that a 2, which changes this to a 4. 1 root 3 implied minus 4 root 3 is negative 3 root 3. Keep the common denominator of 2. Yes, okay. And then example 4. The latitude of it, okay, so these next two examples try to give you some more application of when this might be helpful. The latitude of a point on Earth is the degree measure of the shortest arc from that point to the equator. Okay, this is wordy. So you've basically got your sphere, and it's saying from the equator. So from the center, here's my equator part, and it's saying I'm going to create an arc. So here's my arc that I just cut. So the latitude of a point on Earth is the degree measure of the shortest arc from that point to the equator. The latitude of Los Angeles is 34.05. So we're putting in here 34.5 degrees. Oh, 05 degrees. Crammed in, you can't read that, but that's what it is. North of the equator. Okay, so I instinctively drew it this way, but this is where I knew that it should be going up because it said north of the equator. It should have continued reading rather than going on instinct. So it could have said south of, then you would have gone down. How far is it from Los Angeles to the equator if the diameter of the Earth is, so the diameter is 7,920 miles. So since I am looking for this actual distance and this arc, I know that I need to work with the distance of the entire circle of the Earth. So the distance around a circle is circumference, and that's pi times diameter. The diameter is 7,920. But do I want the full circle? I only want 34.05 degrees out of, and the total for the whole circle would have been 360. So the fraction piece that I want is what this would divide out to be. Now, if you're following the book, they said to change this over into, and this is why this lesson is embedded in here when we started talking about radians. When you're dealing with super small degrees, they say it's better to convert it over to radian. And I'm saying it doesn't really matter. You should get an answer that's pretty close either way you choose to do it. So they are suggesting that here you take the time to do 34.05 degrees over an implied 1 and convert it to radian, which would put the 180 degrees down here to kill off degrees and put the pi up here. And then do 34.05 divided by 180 and say whatever that decimal is, radians over here. So you would have, I don't know, I'm going to make up something, 0.0003 pi for the radians. And then your denominator for the overall full circle in radians is, as we did in the other two, pi when I wrapped all the way around. And then the pi's would cancel off and you're just dealing with these. And that's why they say it's a little better. Either way, you're still dealing with decimals. I don't see the massive difference. And either way, you still have this pi. Oh, there's the other reason why they do it, which I'm going to use on my calculator as 3.14. So however you choose to be doing these, it should work out pretty well. So I'm going to do on the calculator 3.14 times 7,920 times 34.05 and divide it by 360. And hopefully I'm going to get somewhere around 2,352.24 miles is how far that distance should be. Now, depending on whether you changed it to radian or you didn't end up multiplying with the 3.14, you did the pi button on your calculator, which is going to have many more decimal places embedded in it, you might be off here by a bit, but if you're in the ballpark, we should be good. All right, and one more application. Example 5. Theo measured the angle between the base of the building and the top of a building. So here's my building, and it's being measured, received a reading of 0.6 degrees. 0.6 degrees. And again, because that's so small, they say it's best to change it over to radian. Either way. Okay, reading 6 degrees. Theo was 4,000 feet from the base of the building. So this distance is 4,000 feet. And how high is the building? All right, so it's saying that if you find, all right, I'm going to add this arc here. If you take this as part of a big circle, this straight line is almost the same as the curve because this is so tiny. Now, if this was a much larger degree, you would have more of a gap as I've drawn it here, but I drew it a little more exaggerated because I wanted you to see it. In the book, it shows just how tight it is. So it's saying if you find the length of this curve, it is close enough to the length of the straight line. So again, we're going to do pi times diameter. Now this would end up being the radius because that's from the center of the circle over. So my diameter would be 8,000. And then I don't want the full circle. I want only 0.6 degrees out of 360 degrees. And then multiply all of that together, and they're saying you get 41.89 feet for that answer. Now, if you had done it in radians, you would have had your pi, your 8,000, and then you would have had to have converted 0.6 over an implied 1 times you want the pi, you don't want the 180 degrees would cancel off. So you would have here, well, I'll just write it, 0.6 pi over 180. And then see, again, if you have pi and pi, you're going to get pi squared. I just think that's easier. All right, now, totally switching gears, forms of linear equations. On page 282, they go over the different forms for these lines. So you have a general form for a line, and I would have these in my notes for sure. And it is a number with an x plus a number with the y plus a number that doesn't have a letter with it, and it equals 0. So general form always equals a 0. Slope intercept, you already recognize as the y equals mx plus b. Now, how does this terminology help me? M, slope, intercept is the b. That's how that wording equates to this. Then we have what might be a new one, double intercept form. It takes the x and puts it in the numerator and has a letter a underneath it plus y over b, and it equals 1. So double intercept equals a 1. It equals a 1 because you've manipulated this formula by moving the c over and dividing everything by c, and that's why you end up with fractions, because you divided stuff by whatever the number over there was. So double intercept form, you just kind of have to memorize it. Now, the next one is point slope form. So the point implies that I am filling in a point, and the slope means I'm going to have an m in my formula. So with my y, I will minus whatever the point value was So I've got obviously an x and a y. So because I'm dealing with the point, I'm going to be subtracting whatever this number was. So they write that as this is literally the letter y, and this next part will represent the number coming from here. So they call it y1 because it's supposed to be the number, equals, and it's matching this format, so y minus this equals m multiplying with, and the same thing is happening, x minus this number, so minus x1, and then we don't have our b in this format either because it's basically just your slope and your point being filled in. The b is there, it's kind of embedded and implied in here. We'd have to do some manipulation to actually find it if we needed it, but this is the format for point slope, and I hope that that explanation is helping. And then the final one is 2-point form. So as that implies, I'm going to be given 2 points, and so in my work, this is identical, y minus y1. Sorry, I said in my work, I meant in my formula. Instead of being given the m for the slope, I have to find it using the 2 points. Oh, well, that was that formula for finding slope. So that was y2 minus y1 over x2 minus x1 to find the slope, and it's still multiplying with this x minus that number. Okay, now that you know the different formats and hopefully can understand based on the wording why you're being given the formula you're given, it says in example 6, write y equals negative 7/3 x plus 1/5, which is in point slope form, slope-intercept form. And it says, put it in general form, and the integers are the constants. Okay, so we want to get it in general, which means equals 0. So that tells me how to start manipulating this. Make it equal to 0. So we are going to move the y over, and I'm going to write this as equals 0 at the end. So negative 7/3 didn't move on this side, and just because I wanted an x and y and then the number, minus y moved to this side, plus 1/5 didn't move anywhere, I just wrote it again, equals, and then the 0. So just because I like it in a better feel that way, I'm organizing it as I go. Now, I have it equal to 0, but they don't want it with fractions. That's why it's telling you as constants. So what is the common denominator between these? 3 and 5 makes 15. So we're going to multiply this entire problem by 15. 3 goes into 15 5 times. 5 times the 7 is negative 35x. There's nothing here, so it needs the 15, so minus 15y. 5 goes into 15 3 times. 3 times 1 is 3, and 0 times 15 is still the 0. Now, I have mine with complete opposite signs from what the book has. They prefer your x's and y's not be in negatives. There's nothing in general form that says they can't be. It's just a mathematical preference. So they change all of the signs and make this one positive, this one positive, this one negative, and of course the sign on 0 does not change. So this is the final answer that they're going to give for general form. Example 7, use the point slope form of the equation of the line whose slope is negative 1/3 and it passes through the point negative 2, 5, and then turn it into general form. So we are supposed to fill into this equation. So I know that that's the letter y minus the y's number. So they gave me negative 2, 5, so the y number is 5, equals, they told me the slope was negative 1/3, and then x minus the x number, which is minus 2, so that's going to change that to positive 2. Now it was in that format, I'm done. And it says change it to general. General needs to equal 0. So before I make it equal to 0, I'm going to go ahead and distribute this. So let's keep y minus 5 equals negative 1/3 multiplies with x, negative 2/3. Now I've distributed. Now let's move things around. So equals the 0 because I prefer that at the end. My minus 1/3 x didn't move, it's still on this side, minus the y because I did move it, plus the 5, because I am moving it, needs to combine with this like term, so the common denominator is 3. So then negative 2 plus 15, so positive 13 thirds equals the 0, okay? And I don't want it with the fractions. Okay, I was just making sure I was reading it right. Common denominator is 3, so this becomes negative 1x or x minus 3y. And then this 3 multiplies and kills off the denominator, so keeping positive 13 equals the 0. Again, they're not going to like that with the negative, so they're going to change it to positive x plus 3y minus 13 equals 0. And now a final example, 8, write 2x minus 3y plus 4 equals 0, so it's in general form, in double intercept form. Double intercept, so I want it to equal 1. So having these memorized this way helps me understand how I need to begin to manipulate. So if I need it equal to 1, I need the 4 to move over. So 2x minus 3y equals negative 4. And now to turn that into a 1, I divide every piece by negative 4. So this reduces to negative 1/2. And since I know this format has the x in the top, I'm going to write it in that form. It's the same as saying negative 1/2 x on the side, but I want it here because I know where I'm headed. Negative over negative makes it positive. And then this is still 3/4 y. All right, so since I'm going to write it with y over, okay, here's my unique little manipulation. To get the y alone in the top, the 3/4 fraction needs to go to the bottom, and when it does, it flips over. So this becomes over 4/3, and then it equals 1. Oh, and the only other thing they changed was because they had the number here at the bottom, they're actually writing this as x over negative 2 plus the y over the 4/3 equals 1, just to keep it with the number there, just keeping it clean. This is okay, but it's not clean for that format. And there's the final answer for that one.